Welcome back. This is section 7. This is day 3 of your e-learning. In section 7, we're going to tackle what we do when we notice there is an arithmetic series and how we can take some shortcuts in adding all of the terms in an arithmetic series together. We're going to learn a new formula. Just a reminder, an arithmetic sequence is a sequence that has a common difference. That common difference could be positive or increasing or negative and decreasing. Noticing that a series is arithmetic gives you a huge advantage in adding all the terms together. An arithmetic series, if it's infinitely large, will have an infinite sum. Either will approach positive infinity or negative infinity. What we're going to do here instead is not add an infinite number of terms in an arithmetic series together. We're just going to add a finite number of terms. This is something called taking and finding a partial sum. Because the series does not end unless it has a terminating value for the index, that we can't possibly, and there's no real reason why we should add an infinite number of these terms together. So we're going to add just a part of that series together. What we're going to do is we're going to use a formula to do this. We will discover this maybe in a bonus feature. We'll discover why this is true. And maybe I might explain it with the second example because there's a really neat thing in that second example when we get to it on how this formula might have been discovered. So in order to use this formula, there's a lot of terms and different parts and components that this formula has, and some new notation. This S is of course, the capital letter S is going to represent our sum. The sum of how many terms, the n indicates how many terms there are in the series that we're adding together. So if I'm adding the first 13 terms in this series down here, then this would be like a S sub 13. So when we get to the bottom, what we're going to do is we're going to find the value of the first 13 terms if we were to add them together. Since n is the number of terms in the series, we actually use that value in calculating the partial sum. We would use that here and divide it by 2. Why divide by 2? I guess that's because it just works. A sub 1 is our value of our first term. So it's not the first term in the sequence, it's the first term in the series. And don't get that confused. The first term in the series that we're adding together. So we're going to put in the very first term in the series and the last term in the series. That's what A sub n represents. So let me go back to the start. S means we're adding together. N is how many terms we're adding together in an arithmetic series. That value of n, how many terms, gets divided by 2, and then you multiply that by the sum of the first term and the last term in your series. Okay, getting to the bottom here. So this formula will work if we knew all those pieces to it. Since we're adding together 13 terms, how do I know that? We're going to start with the first term, the second term, the third term, all the way up to the 13th term. I don't need to count 1 through 13. That's 13 terms. So 13 gets divided by 2. Now what is the very first term in our series? I remember this one from the last page. Plug the value in for 1. In our index, -5 times 1 is -5, plus 25 makes 20. The very first term in the series is a 20. This has a value of 20. Then we're going to add to it the very last term in the series. Now the last term index is 13. Plugging in 13 here gives me -5 times 13 is -65, plus 25 more gives me -40. So let's go to the formula. Let's see how we're going to do this. If I add parentheses first, 20 plus -40 makes a -20. And without a calculator, if I'm going to multiply 13 divided by 2, I get a decimal, but what I can notice is 2 does go into 20 10 times. 2 goes into 20 10 times, so 2 will go into -20, -10 times. Now I'm left with a product of 13 times a -10. 13 times -10 is -130. If you recall in the previous section, we did have this question where I crossed out a bunch of terms because they had some opposites. The last 4 terms, these were the terms I didn't cross out. They were like -25, -30, -35, and -40, and that's what gave me the terms in the series that were left over to add together, and it gave us a sum of -130. This exercise here to the right might be helpful for me to explain how we're going to add these terms together. Now, I couldn't possibly fit the 100 terms in this partial sum on the section to the right here, but if I start generating it, plugging in our values for our index starting with 1, I'm together going to add together the number 1, and then the next value would be 2. Plugging in 2, I don't have to calculate anything in my formula. I'm adding 1, and then 2, and then 3, and then, I can't possibly write all these numbers. So I'm just going to put a dot, dot, dot. The ellipses is going to represent all the terms that I, don't want to write. Now I do know that number 100 is the ending index. Before that number 100, I would have to plug in like 97, I'd plug in 98, I'd plug in 99, and I'd plug in 100. So these dot dot dots, that dot 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 allows me to represent the missing terms in the series. And I kind of am noticing maybe something happening here. It seems like if I added a couple of these terms together, like 1 and 99, they make 100, and 2 and 98, they make 100, and 3 and 97, and they make 100. I'm getting a clever way of pairing these terms, but that's not exactly how this term or this formula will work. What the formula says that I have to do is I want to add together my first term and the last term in my series. So I'm not going to add 1 and 99. Instead, I'm going to take the very first term and the very last term and add them together. Then I'm going to go in and add together the numbers 2 and 99 and 98 and 3. What happens when I add 3 to 98, or 99 and 2, or 1 and 100? Well, I come up with the same sum of 101. That sum is what's represented here when you take the first term and the last term in the series. This represents a sum that every pair of numbers is going to have. Now, I use the term pair because what does n divided by 2 represent? That represents how many pairs of numbers are going to have the same sum. So how many pairs of numbers can we make if we have 100 terms? We'll make 50 pairs. I wrote the number 50 here, but I wrote it as n divided by 2. So this represents the number of pairs. N divided by 2 is the number of pairs of terms that we're adding together. The second part of this formula, a sub 1 plus a sub n, represents the sum of every pair because every pair has the same sum. I'm going to multiply these together, and when I do, I get 5,050. So this arithmetic series formula works when you're multiplying, or excuse me, when you're adding together a finite number of terms. What you can do is you can count how many pairs of terms you can create, and each pair will always have the same sum. Good luck to you. This concludes section 7. You may move on to section 8. What's going to happen when we change this to arithmetic into geometric series? And everything changes and we can't use this formula. All right, good luck.